Okay, let's take a look at the first approach. This is section 9.1, the least squares approximation, or discrete least squares approximation. Okay, here's the idea. We want to find, let's start with the straight line, okay? The line of best fit, a linear equation or linear function of best fit. Okay, we would like to figure out what this function is, and we know that this is a linear function. It's a straight line, so we'll have this format. Okay, and then basically we want to find what A and B are. So to do that, we're going to consider the distance of points, but actually we're going to consider those points as vectors. So let me show you what we're going to do here. So this would be like the point where we calculate the distance. Okay, so it's the distance from that line, and here is a point on the line that is closest, or that we're going to use to minimize the distance, and here's another point. Okay, so what we're going to do is to take these values. So this one here would be f of x1, okay, because this point is x1, y1, so they have the same x value, right? So maybe I should do this way, x1, f of x1, and then this point here would be x2, f of x2, and that point is x3, f of x3. Okay, and then we're going to calculate the distance. So how are we going to do that? Well, we take we consider two vectors, the y1, y2, and y3. Okay, this is vector 1. Here's another vector, u, that is these y values on the line. So this would be f of x1, f of x2, f of x3. And then we simply calculate the distance. Well, the distance would be norm, right? Norm of u minus v. So it will be something like this. Now, if you remember from calculus, or eventually we'll see that in two dimensions is easy. It's the distance between two vectors, 2 points. In calculus 3, we'll see the distance between 2 points in the 3D space. But anyway, this is the square root, right? Subtract y1 minus f of x1. So let me do it the other way. It doesn't matter because it's squared anyway. Minus 1 squared. And then f of x2 minus y2 squared plus f of x3 minus y3 squared. Okay. And what we're going to do is to minimize the distance. We're going to do xd squared, and we're going to minimize the square of the distance. So we can call this the new d, okay? Okay, how do we minimize we want to minimize d. And d is a function of several variables. Let me show you why. So if I take d here, you will see that d is, in fact, if you expand this formula for d, f1 is ax1 plus b minus y1, right? Because remember, f of x, that's this function here. We're trying to figure out a and b. Okay. And then if you expand the second one, that would be ax2 plus b minus y2, and then ax3 minus plus b minus y3 x squared. And the variables here are a and b, right? We're trying, see, the d is a function of a and b because x1, x2, x3, y1, y2, y3, they're given numbers, or they already given, and we're trying to figure out a and b. So the trick here is to use the minimization process in calculus. In calculus 1, when we try to minimize a function, we take the derivative, right, and we set the derivative equals to 0. When you get to calculus 3, you will see that the minimization of a function of several variables has a similar approach. So we set what we set partial derivatives equal to 0. Partial derivative means it's a derivative of d with respect to a. Okay, we set that. So this is the symbol for derivative. Partial derivative means that you're going to take the derivative of that expression there and in terms of a, and you set that equals to 0. That's all it means. And you're going to set the derivative of d with respect to b equals to 0. So when we do that, let's see what we get. Okay, so this one here will give me, okay, what is the derivative of this whole expression with respect to a? Okay, remember product rule, right? We derivative of that expression, we bring the 2 down, and this would be ax1 plus b minus y1 times the derivative of what it's inside. It's a derivative with respect to a, so the derivative of what we have inside, that's x1. Okay. And plus, then same thing with the second one. This is ax2 plus b minus y2, oh no 2 here, times x2, right? Bring the 2 down, subtract 1 from 2, and then derivative of what you have inside is x2. Same thing with third expression there. And then we set this equals to 0. And you're going to do the same thing with the second one. Take the derivative, but now it's with respect to b. Let's see what happens. Bring the 2 down. Now the derivative of that expression with respect to b now is the variable. Derivative of b with respect to b is just 1, right? So times 1. And then it will be the similar process here. x3 plus b minus y3 times 1 equals to 0. So there we have it. We have two equations, And this is pretty nice because we have two variables we need to find, and we have two equations, so we should be able to solve for A and B. So if you simplify, if you combine terms, move terms to the other side, and if you simplify these two equations, eventually you will get something like this. Let me write this for you, here for you. And here it is. If you collect all terms, right, here's x1 times x1 is x1 squared, so it would be 2ax1 squared, and then 2ax2 squared, 2ax3 squared. Combine all of that, here it is. Same thing with the 2b, right? You have 2bx1, 2bx2, 2bx, I'm missing x3 in there, right? Yes, I'm missing an x3 here. Yeah, when I took the derivative, I forgot to put x3 here. Yeah, so here it is. And then there are terms that have the x and the y together, right? 2ax1, 2x1y1, it's negative. See, that's why I had the negative here. And then down here, let's look at the second equation. You have 2b, 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 2b 3 times, so that's 6b. And then there's y1, y2, y3. It's negative 2, right? Negative 2y1, negative 2y2, negative 2y3. Okay, so that gives you the system, and that system becomes simply, we can rewrite the system in this format, right? Summation from I from 1 to 3 of x1, not xi squared, right? That's what this is. Plus, see, the first equation, I can divide the entire equation by 2, so I can move this out, the 2 out, and then plus b, summation of the x's from 1 to 3, and then move that on the other to the other side. That gives me summation of xy, yi, 1 to 3. And then down here, I could divide the entire equation by 2, so I get a, then I from 1 to 3 of xi, right? That's what that is. Here is simply 3b. Let me write this way so you have the coefficient will be times 3. And then on the other side, you have summation of y. So that is a system. Now it's a 2 by 2 system. 2 by 2, you get a 2 by 2 matrix, coefficient matrix. So it's very easy to solve. So you can, by the way, they have special names, okay? So this guy here, they call it SXX. So SXX is a summation of the xi. So if you have 3 points, then it will be 3 summation of 3 x's there. So let me go ahead and put it this way. So n is the number of points. And then you have s x, which is a summation, oh, I forgot the square here, 1 to n. And then you have the other is the sy, summation of the y's, 1 to n, forgotten one, sxy. That's for this term here. going from 1 to n. Okay, so if we do that, our system becomes simply sxx plus bs sx equals to sxy sx plus b times 3 equals to, I want to show something here. This 3 here is the n, okay? Because in our case we were using 3 points, so that's why you see the 3 there. Just a side note here, this is n. And then here's sy. Very easy to solve this system. Coefficient matrix sx sx and then here's 3. You could use Gaussian elimination or any other numerical method that we used before. But because this is a 2 by 2 matrix, we can go ahead and put a formula for that. You know, there's a formula. You all recall formula? A, B, C, D, inverse. So that's the determinant, right? 1 over the determinant. And then we swap D and A here. And then opposite of B and opposite of C. Right, that's a formula for the inverse of a 2 by 2 matrix. So we can go ahead and use that. So our A and B can be found by simply doing that. Let me see what I have here. Yeah, okay. Well, 1 over the determinant. Now let me call this A. So the determinant of A times 3sxx minus sx and times sxy sy. So this is how we found A and B. So f, the function that we wanted would be ax plus b, right? A and B found from this. So this is in the book, the program for that. That's on page 338. C octave program on page 338. Okay. Now, when you try to find the approximation using a quadratic function, right? The quadratic function of best fit, you would do a similar approach. So instead of using, here, let me go back here, and instead of using the linear function, right, we use a quadratic function. So let me go ahead and finish that and show you the idea. So for quadratic, of best fit. So we would have this formula here. But instead of that, and then I would do ax1 squared plus bx1 plus c. And then ax2 squared plus bx2 plus c minus, I got the minus there. And then ax3 squared plus bx3 plus c. Okay, so again, we set partial derivatives. Partial derivative of d with respect to a equals to 0. You set partial derivative with respect to b equals to 0, and derivative with respect to c equals to 0. So you're going to get 3 equations, and now we have 3 variables, right? We have a, b, and c. So you will have that same format of type of system, and that is also in the book. So I'll let you take a look, and let's see where this is. Yeah, this is on page 342. See page 342. Okay. So you will have a system that will look like this. Let me write down. You have A, and then S. This is SX4, and then I'll show you what those are. SX3, SX2 equals to SX2Y. I'll explain what this is in just a minute. And then look at the format. There is a certain structure that is easy to remember. And then here is simply SX. One more equation. SX2 plus B SX plus C times N. Oops, this is SY. See how the structure is? You have SX4. SX4 means SXXXX. Right? It really means a summation from 1 to n of xi to the 4th. Okay, so x3, that would be sxxx. That's summation from 1 to n of xi cubed, and so forth. So look at the structure. You have sx4, sx3, sx2, and then sx2y. The second equation, you're going to kind of shift to the left, right? The sx3 now is here, the sx2 is here, and then here it's sx. So x3, 2, 1. And then sx2, sx1, and then there's no such a thing as sx0, but in fact this is actually n. So, and then you have a matrix, a 3 by 3 coefficient matrix. Now that is hard to solve directly, so you need to use some type of numerical method to solve the system. So in that case, you could use the G pivoting, right? The Gaussian elimination with pivoting. So if you look in the book on page 4, so see page 342. If you look in the program, the program uses the backslash. So this is the matrix A, and then to solve for A, B, and C, use the backslash operator, which in Octave is much faster. Um, or you could use any other Gauss elimination with pivoting, or even the iterative method, Jacobi, or any other method. But in that case, I think the backslash, because now Octave is updated, it has a good numerical scheme behind the backslash operator, and so it's much faster. Okay, so this will give you the A, B, and C, and that will get you the quadratic equation that will approximate those 3 points or whatever number of points you have.